this molecule reacting with triethylamine. You know, triethylamine is a bulky base. And then we're expecting something. But the thing is, I didn't give the structures. What I gave is a meso. So the question is, what is meso? Did we ever talk about meso? And then so it's yes, we did, even though you made introduction. So what is a meso? Meso is a molecule with the chiral centers, but the whole molecule not chiral because of symmetry. So this symbol, the phi, again, organic chemists are very lazy. You have to, you can draw the benzene, or you can write this pH. Sometimes writing down the pH is too much work, so they just go like this phi as the benzene. So I know it's a very lazy habit, but this phi symbol means a benzene, the phenyl. So you can expect a benzene here, benzene there. But the thing is, I'm just drawing the feature projection and showing you that what's meso. You can draw, these are two steric 4 possible isomers, but you're not going to get the 4 isomers because there's a plane of symmetry in the molecule. This molecule with a plane of symmetry, that's a meso. The other two is all RNS systems. You're going to point out which one's which. But the meso is a special one, the one with the symmetry. That's a meso. We're talking about this one. Going through the reactions with the base, then it's going to make a double bond. So what products you're going to get? That's what this question is about. Well, there is a bromine you can kick out. To kick out that bromine by making the double bonds, do we extract this hydrogen or that hydrogen? It's got to be adjacent carbon, hydrogen adjacent carbon, not the hydrogen of its own. So this hydrogen, if you take it out, this bromine is going to go make a double bond. But we got another hydrogen up there. When you take this hydrogen, you're going to make a double bond, you're going to keep this double bond, bromine is out. So there's two possible ways that's making alkenes. So when this type of two possible way, what we need to do, we should do both and figure out what are made from each process. So what we're going to do, I'm going to redraw this one. This is a Fischer projection. All the horizontal line is coming toward you. All the vertical line is going away from you, right? That's the conventions. I mean, you can probably assign the RNS system, so, make sure that you draw the right one. But this is not enough. You have to show the hydrogen and the bromine as an anti-coplanar before even considering E2 elimination, right? So we got to redraw. We need to redraw. I'm redrawing for this hydrogen, I circle the blue circle, and then this bromine down there. That's the first thing I'm going to do, and I'm going to do this one later. This hydrogen, this bromine, I just put in the line, means that they are anti-coplanar. I have to redraw all the things around and make sure that there's an R configure, which is what it is, which is what it does. And the other side, this phenyl and the hydrogen has to be displayed to make an S configure like this. So it's need a lot of checking to make sure that you draw the right configuration, because if you draw it wrong, you definitely get wrong answers. But this is kind of same thing. I put this hydrogen in blue circle and then bromine on the opposite side, anti-coplanar. Now these things are ready to go for the E2 elimination reactor, right? Base come, pick up this hydrogen, double bonds are made, bromines are kicked out. Then where these two benzene going to be staying after the double bonds are formed, they're going to be on the same side, right? So you're going to get a cis molecule. But that's when you're taking this one and that bromine. We need to do the other one. So I need to redraw this hydrogen in the red circle and that bromine anti-coplanar. So I redraw like this, and then I need to make sure that that's R, that's S configured. So I need to redraw that. So a lot of redrawing correctly, you should carry it out. Otherwise, you get the wrong answer. But if you do that, you're going to get this. Then you take this proton and then double bonds form, bromines kicked out, anti-coplanar fashions. Then you're going to get the double bonds mated, but you're going to get the two of the benzene still on the same side. So that meso molecule, it doesn't matter which hydrogen are pulled up by the base, you are actually getting the same product. So that's make it simple. Now the question I can extend to from this one is, what if you're using this or using that, what product you will get? Are they going to be same like this or are they going to be different? But those are something that I really want you to try at home and figure out what's going to happen. You got the chlorine here, and then adjacent hydrogen. Yeah, that is adjacent hydrogen here, but you know that that one is a opposite side. We allow you to change the hydrogen. Hydrogen is on the same side as the chlorine there. So that hydrogen, you will never gonna make double bonds with it. Only the hydrogen you can pull out by the base is the one here. So you only get this, not the others. Right? So that is something that anti-coplanars are really critical. So I'm pretty sure that that's something that we discussed so many times. You know what it is. And the question is kind of combining to these type of things. I mean, we haven't really talked about the fused bicyclic systems, but that's the reason I'm going to show you like this. This is called decalin. Decalin is a two 6-member, two cyclics hexane kind of fused together, sharing the single carbon-carbon bond. So this is decalin. These two can go elimination reactions. Each elimination reactions, one was found. This one goes faster than the other one. So why? That's the question. For each elimination reactions, anti-coplanar conformation is really critical. So we're going to show what's the most stable conformation of this one and that one. This one, how to draw the chair conformation, the fused bicyclic. This is going to be a chair, that's going to be the chair. Sorry. So this chair, that chair, you put it together, sharing this bond. That's going to be the most stable conformation of decalin. You can imagine that. And then when you place all the substituents, this one's down because it goes down. And then the hydrogen here, I mean, the bromine is down because it's right here. That's the axial. So this bromine already taken axial. You got those two axial hydrogen and the coplanar, so they can make an elimination reaction anytime. So that's it, basically is ready for the each elimination reaction to happen. The other one, on the other hand, if you look at the most stable conformation, the same way you present the carbon skeletons, this bromine is going to equatorial. Conformationally, it's more stable, but the reactivity is bad because this is not ready for the each elimination reactions. In order to make the each elimination reaction, you got to flip the chair to make this bromine axial. That's what you need to do. But when you make this bromine axial, this whole carbon chain is going to stick it up. This whole thing is going to axial. That's going to create huge state hindrance, which makes it energetically not easy. So that's the problem. So because of that, this molecule goes through each elimination very slow. Because this conformation, the only allowing each elimination reactions is not stable one. It's a much less stable because the huge cyclohexane ring is being both axial makes it stably very hindered. So that's the things, these questions are asking, which ones are more ready for each elimination to happen, which is the anti-coplanars. When they're built in the most stable conformation, it's all ready to go, fast reactions. But if it's not, then it has to wait until it's converted to that. But that's kind of not happening easily. So only a small number of time they go up, then makes a reaction happen. But most of the time they stay in this form. So no reaction there. So that's why the whole thing goes slow.